Hi, I'm Alon Rosen. I'm the chair of the first session. We are a bit behind the schedule. Speakers have 15 minutes in total, 12-minute talk, 3 minutes questions. First talk is by Changui Mu on instance hiding interactive proofs.
Nice. Okay, thanks Alon for introduction. Thanks for attending my talk today, everyone. My name is Changui, and today I'm introducing our study about instant hiding type proof. This is joint work with my supervisor, Professor Nalini Vasudevan. Interactive proof is a fundamental notion in cryptography. It's a protocol where a stronger prover interacts with a weaker verifier to convince the verifier that a proposition is true. In interactive proof, both parties may hold some secret that they do not want the counterparty to learn through the interaction. One of the most beautiful and influential examples is the knowledge proof. It protects the prover's private information, such as the MP witness, against the verifier. And in some other case, the verifier may also hold some secret. And one of the most natural secrets of the verifier is the input instance. And this is when we need instant hiding type proof. So in instant hiding type proof, or HIP, in the beginning of the protocol, the verifier is given the instance as input, while the prover is only given the length of the instance as input. We ask for standard completeness and soundness. This means if the instance is in the language, then honest prover make a verifier accept with high chance. But if the instance is not in the language, then no prover is supposed to make a verifier accept with a high probability. In addition, we ask for this instant hiding property. This means for any prover, there exists a simulator such that for any instance, the simulator only takes the length of the input and the simulator distribution, that is epsilon close to the prover's view in the protocol on that instance. Here, the simulator may not be even efficient. And to denote by HIP the classes of language that has such an instant hiding type proof. The existence of instant hiding type proof seems quite counterintuitive, because how can you make a proof without even knowing the statement that you're proving? Here I'm giving a simple example. So consider a cyclic group with a generator G, and define the language to be the set of group elements whose discrete laws most significant b equals to 1. And this language has a simple HIP. In the beginning of the protocol, the verifier is given a group element as the input, and there will sample some random r from possible group orders, and the set x prime equals to x times g to the r. So essentially, x prime just some uniform group elements independent from the input instance. The verifier sends the x prime to the prover and asks the prover to compute the discrete law for it. We denote by z prime the discrete law of x prime. If the prover behaves honestly, then z prime minus r is supposed to be the discrete law of an input instance. So the verifier can check that and verify the most significant b. We notice that the protocol is perfectly complete and sound, because here this z prime minus r serves as the MP witness of this input instance. And it's also perfect instant hiding, because the distribution of x prime is independent from the input. So the prover learns nothing about input at all. Moreover, for this particular language and this particular protocol, the distribution of x prime, z prime is efficiently sampleable. This means that we can efficiently simulate the honest prover's view. And for this special case, we call the simulatable HIP. On the other hand, if the verifier's view is efficiently simulatable, this is known as the knowledge proof. And the statistical knowledge proof is when the simulated distribution is statistically close to the verifier's view as in the protocol. In the last few decades, there were many great work on understanding the complexity and application of the knowledge. The knowledge proof has become the foundation and will continue making difference. On the other hand, our understanding about instant hiding was much less. So in this study, we want to understand instant hiding type proof, the power of it, and the most natural question is whether all MP problems can have an instant hiding type proof. We also want to understand the relationship between HIP and other cryptography primitives. We found many similarities between the two classes, the HIP and the SCK. Thus, we spend some efforts to understand the relationship. The next, we want to understand the closure property of HIP, whether it's closed under negation, repetition, etc. In the end, we also want to understand whether this class has a natural complete problem. For the first question, the upper bound, previous work done by Abadi, Feigenbaum, and Kilian show that perfect instant hiding HIP is a subset of NP/poly intersect NP/poly. This means that NP complete problem is unlikely to have a perfect instant hiding HIP unless polynomial hierarchy collapse. The result, however, cannot be extended to the general HIP. And in this result, in our work, we extended the upper bound to any epsilon HIP where the instant hiding can be as large as some constant. This means NP complete problem is unlikely to have such instant hiding type proof, even relax this hiding error to constant. And for semi-mutable HIP, we can remove non-uniformity and show that semi-mutable HIP is a subset of AM intersect co-AM. Similar results were found for SCK, so NP complete problem is unlikely to have neither SCK nor HIP. Next, we show that some hard HIP will imply one-way function. In particular, we show that if any language that is hard on average and has constant round HIP, then there exists infinite often non-uniform one function. For the semi-mutable HIP, we show a worst-case simplification. We show that if any language that has just a worst-case hard and has a semi-mutable HIP, then there exists a one-way function. There was similar result found for SAK and the other influential notion, SRE. And by looking at the table, it's very interesting to find out that from complexity point of view, the simulatable HIP with respect to HIP is kind of an analogy of SRE with respect to SAK. And indeed, in previous words, mentioned that the instant hiding type proof can be viewed as a special version of an interactive version of randomized encoding. So given the similarity between the two classes, SCK and HIP, it's natural to ask what's the relationship between them. So we answer the question partially by giving an oracle separation of HIP from SCK. In particular, we show that there exists an oracle language that has an instant hiding type proof, but provably has no statistical knowledge proof. In the end, lastly, we show that the HIP is closed on the polynomial size circuit. This means consider any HIP language L and any polynomial size circuit G. If there's a second language whose membership can be decided by G taking membership of L as input, then the second language L prime is also inside HIP. The similar results for SCK is only known to behold on the polynomial size formula. This seems give another evidence that the two classes are different. So leaving some detail, these are our main results. And due to time constraint today, I'm not able to cover all of them. Instead, I will show the following statement as a bird's-eye view to our hard HIP invocation to one-way function. So I'll show that if any language that is average case hard and has a one-round simulatable HIP, then there exists a distribution one-way function. So what is average case hard? With a language is hard on average, if there exists efficient samplable distribution, such that if we sample instance from that distribution, no efficient algorithm can solve the problem better than a negligible advantage. And the distribution one function and all those functions, roughly speaking, those functions that are easy to compute but hard to invert uniformly. So if, leaving some detail, if some efficient function is not distribution one way, then there exists efficient inverter that takes the random image and invert the pre-image uniformly. In the one-round simulatable HIP, the very fast view is composed of the instance, its own random C, and some public transcript. Here, because we have this efficient simulator, we can sample previous view efficiently. And notice that the public transcript is also part of honest previous view. This means that we can sample everything inside the very fast view except the random C. Suppose we can sample everything inside the very fast view. By completeness and soundness, we can decide language efficiently, which will conflict our assumption that the language is hard. So indeed, in the we will try to construct some candidate function and show that if this function is not distribution one way, then we can sample the varchar view efficiently. In particular, our function will be like this. You will take an instance and the varchar random C and run the varchar algorithm to generate its first message. The output distribution of the function is supposed to be just the instance and the varchar's first message. And suppose the function is not distribution one way, then we have an efficient inverter that takes the instance and the message and help sampling a random C that is consistent with this instance and the transcript. So if we have this inverter, we can do the following. We can run the simulator to generate the public transcript, and we'll run the inverter to sample the random seek. And this is exactly the varchar view, which will let us decide the language efficiently and contradict assumption that the language is hard. Therefore, the function must be distribution one way. This argument, however, cannot be extended to two-run. Let's see why by looking at the two-run protocol. So recall that before we assume there's no distribution one-way function, we can basically efficiently invert any efficient function. And we want to use varchar's algorithm to make the candidate function. But in the two-run protocol, the only message that we can efficiently simulate is still just a first-run message. That means following the same argument, we can only get an inverter that sample random C consistent with only the first run, which is insufficient to simulate the varchar view. What we really did is a non-constructive proof. Intuitively, we use the adversary or the inverter in a non-biased way to make a second candidate function, and we'll show a win-win paradigm that either the function is a distribution one way, or we get a better inverter that will allow us to decide the language. So the proof of rest of result are more self-involved, so we refer our audience to our paper for detail. For the future, we have a few interesting questions. And the most intriguing one is to understand whether this HIP class has natural complete problem, like a SCK, which has very beautiful complete problems. Yeah, so that's all from my side. Any question? Oh, yes, that's a very good question. So firstly, we don't know. We don't know how to construct this order separation. Secondly, we also don't know how to make a HIP for some very natural SAK problem, such as a statistical difference problem. We don't know how to make a HIP protocol. Yeah. Thank you for your question.